let's just first talk about something that looks continuous. Is this cute little x squared graph continuous?
Yes.
Agreed. Because did I have to pick up my pen to draw it? No. Is this gun continuous?
Yeah.
Yeah. Cute little x cubed graph. I never had to pick up my pen. What about this one? It's also continuous, right? So you're like, cool. I'm good with continuous. Let's look at 3 examples of something that's discontinuous. We've got 3 different words: infinite discontinuity, jump, and point. And these are 3 words that we will use in AP Calc. Why do you think this one is considered infinite discontinuity? Where are my Y's going to?
Infinity.
They're going to infinity, aren't they? So do you agree to draw this graph? I wouldn't be lifting my pen, and then I'd have to lift my pen and put it down and come back. That's why this one's discontinuous, okay? Because my Y values are going to infinity, that's why it's called infinite discontinuity. Cool? Okay, what about this guy? Why do you think they're calling this one jump? Because when I'm drawing this graph, and then I literally have to jump and lift my pen to continue drawing that graph, right? That one's called jump. Anyone want to know why we call this one point? It's just missing a point, right? It's missing a hole. It's got a hole, rather. So anything with a hole is going to be point discontinuity. Anything where we have to literally jump, it's pretty self-explanatory. And anything with a vertical asymptote, because that's what's going on here. We've got a vertical asymptote, so my Y values are going to infinity. That'd be infinite discontinuity. So it says, this is the stupidest blank I've ever had. If a function is not discontinuous, then it's continuous. Who does that? I'm sorry. I don't know what I was thinking. Not discontinuous, that's like double negatives. We're not having fun. You know what I'm saying, Mateo? Okay. Linear functions and quadratics are always continuous. And here's where we're going to learn a little lingo. Maybe Daria could even tell us. Daria, if I wanted to know, could you read to me out loud what I'm writing right here?
The limit as x approaches c from the negative side is something.
What do you think, Dar? Do you think it would be equal?
What, equal to positive?
Yeah.
Yeah, it's continuous, yeah.
Shoot. As Daria said, we're curious, what happens to my function as I approach the C value? Here's this new lingo. We've got room underneath it, so let's write it here. We're going to say LIM for the limit. And then we're going to say as x not equals c, we're going to draw an arrow to the right. You're like, what? I don't care what the value is at c. I'm curious what the value is going to be as I approach c. So I'm going to draw this arrow in as I approach c. And then we do this little superscript of a negative. Like, what is happening? And that just means coming from the negative side or the left side. And on this picture, we're going to say then that equals the limit as x approaches c. And again, if I'm coming in from the right side then, anyone have any idea what that superscript should be now? A positive. Now, it's not asking what's the value at c. It's not saying x is c, what's that y value? It's saying as I come in, basically the question is, where do my fingers touch? Do they touch? So it's saying from the left and from the right, what value do my fingers come together at? So for something to be continuous is no longer like the algebra thinking of, did you lift your pen or not? We've got to see if it passes these three requirements. The function is defined at c, meaning when I plug in that x value, we get a point. So let's go do that real fast. Or let's just sketch this. 3x squared plus 7. What's my parent function look like with our arms? Boom. What's that plus 7 doing? Up 7. What's the 3 doing? Skinnier. So let's just go like this. Whoop. That's what that graph looks like. My question is, do we think that this graph is going to be continuous? Yeah, the first thing we got to just make sure, does f of c exist? Does f of 1 exist? Let's go see what that gets us. What is f of 1 going to be if I plug a 1 in right there? 10, right? 3 times 1 squared plus 7, that's just going to get me a 10. Then what I'm going to show you next is very funky. Actually, on this one, I'm good with saying it's going to be continuous. Let's prove it on something that looks a little weirder maybe. Continuous. Just because we know what a parabola looks like, I'm going to say it's continuous. Let's go talk about this one that's going to look a little funkier. Koopy got his calculator out, and I'm good with that. Let's go to our calculator, you guys. Let's go graph x minus 2 over x squared minus 4. X minus 2 over x squared minus 4. When we did zoom decimal, what they put right here? Isn't that hole? If you did zoom 6, that hole's not going to be there. You can only see holes on zoom decimal, unfortunately. Like on my calculator, do you agree? It does not look like there's a hole there. You know what I'm saying? So it's very misleading. Zoom 4 to do the decimal. Since they're asking, hey, is this continuous? Whoa. Is this continuous at x is 2? Doesn't it look like there's a hole at x is 2? So let's go sketch ourselves a little graph of it. Does not need to be perfect. Where does it look like there's a vertical asymptote? Agreed, at -2. Boom, boom, boom. Vertical asymptote there. Then there's a hole at 2, and it looks like, I don't know, about there-ish.
Yep.
Cool. Thanks, Beck. Then we can do this. And then we can do this. Okay, check this out. What if I were to say, is this continuous at 0? Do you think at 0 this graph looks continuous? Yeah, how about at 1? Yeah, it looks pretty good, right? It's not going to be continuous at 2. We got to be able to prove it without a calculator. Here's how we do it. First, we got to go make sure f of 2 exists. We got to go plug in 2 into my function. Wouldn't it get me 2 minus 2 over 0, 4 minus 4? 0 over 0, is it going to exist? Can we do 0 divided by 0? No. So we can just say that does not exist. As of right there, we would say discontinuous. Because my function doesn't even exist at that point. You guys, look at this next one. This is a lot. How do I even graph all that, right? We just do one at a time. Let's just focus on what does 1 over x looks like. If I focus on just this part, I'm going to just graph that guy, 1 over x. So I'm going to go y equals 1 over x. You might want to go back to zoom 6 just so you've got a normal window. So I graphed just 1 over x, and I did zoom 6. So I'm going to go open circle there because that was greater than. So I've just graphed this part. Ooh. I've just graphed this first function. What does y equals x look like? Nice. Y equals 1x. My slope is up 1 over 1, so it's just going to be an up diagonal line. So that's going to be this line. Where do they care about it? At the open point. From 1, and do I want to keep going to the right or to the left? Since they said x is going to be less than or equal to 1, x is 0 here, x is -1 here, and here's my graph. I colored that one in because it shared that point, and look at this, Beck. It said less than or equal to 1. Yeah. So now, I'm asking, does this graph look continuous at 1?
Yes.
Does it look like I'd have to lift my pen?
No.
Does it look like there's a hole?
No.
No, that hole was colored in because of that guy, right? So, here's what we're going to do first. First, we got to go find f of 1. This is heavy today. I apologize. I wasn't prepared for this mentally. If x is 1, should I plug in the 1 to the top function or the bottom function if x is 1? Bottom, because this is less than or equal to 1. If I plug in 1 in right there, what do we get? 1. Does f of 1 exist? Yeah, it's a point. Boom. First requirement was made. Look at this next thing then. The second, the function approaches the same y value on the left and the right side of x's c. What? That is very crazy. That's when we got to do some of our limit. Let me talk to you one more time. Ready? The limit as x approaches 1 from the left. That's how we're going to write that. This is all brand new, so just give yourself a sec. The limit as x approaches 1 from the left. Do you think that's dealing with the top function or the bottom function? If I've got to approach 1 from the negative side of it, would that be x values bigger than 1 or x values less than or equal to 1? It'd be that bottom one, right? So I'm going to put that function right there. I'm going to put that function right there. Then I've got to go see, is that equal to the limit as x approaches 1 from the positive side? You're like, well, what function do I look at then? Yeah, 1 from the positive side would be x values bigger than 1. So I'm going to plug in a 1 over x there. Let me put that in my pink. Then you're like, okay, how the heck do I even evaluate that? I don't know. Well, you guys, from our graph, as I approach 1 from the left-hand side, here's 1. As I come in from the left-hand side, where does my finger end? At what y value?
1.
1. So on the left side, it's 1. What about as I approach 1 from the positive side? When I approach 1, where does my finger end? At 1. Do those equal each other?
Yes.
Yeah. So the limit, meaning my fingers will come together at that point. The third question is, bummer, the y value. Okay, the third standard is, I need to get all these to lock it in. The third part is, was your answer from the first one the same as your answer from the second one?
Yes.
So how we'd say this mathematically, step 3, is was f of 1 equal to your limit as x approached 1? Was my answer to the first the same as the answer to the second? When we say my f of 1 was 1? We'd say, all right, we got a 1 on that one. And then what about down here? They both equaled 1. Does 1 equal 1? Yeah, so we can say it's continuous at that x value. I just shoved a lot of calculus down your throat. Whoa, do not be discouraged if you're like, dude, I am lost right now. It's okay. It's the first day of it. I just really want to expose us to it, just so that we have seen it once. We'll get there together. Here we go. This guy. Let's go graph these. Let's do this without our calculator. We can do this without our calculator. Where would we start this one? Minus 2. I'm going to go down 2. Then what's my slope? Up 3 over 1. Up 3 over 1. Down 3, left 1. Where do we care about that? X is greater than 2. X is 2 is here. Do I want to draw that line to the right or to the left? Greater than means go to that right. So I'm going to go graph that. I'm just going to kind of extend it, and I'm going to get rid of my other points because they only wanted it to the left, to the right, my bad.
It's open.
Say it again.
It's open.
Yes. And he's saying, wait, at 2, should I make that a closed or an open circle? Got to open it up. So at 2, I'm going to make that a hole. Okay. Can we graph 2 minus x? That's the same as negative x plus 2. Where do we start?
2.
Up 2. What's my slope? Negative 1. Ooh, I went positive. Woo-hoo. Down 1 to the right. Down 1 to the right. Where do they care about that? Good. So I'm going to go to the left of 2. So I care at 2. And then I'm going to go to the left of it. Does this look like it's going to be continuous at 2? It's not looking like it, right? We just have to prove it mathematically. You guys, what is f of 2? Which one would I look at? Top one or bottom one?
Bottom one.
Yeah, when x is less than or equal to 2, I'd plug in a 2 right here. What do we get?
0.
Yeah, we'd get 2 minus 2 is 0. Okay, does f of 2 exist? It can be 0. I'm fine with that. 0 is a number. F of 2 exists. Then in step 2, we got to compare limits. What? I know this is new. the limit as x approaches 2 from the left. That's how we say it. That's how we say it. That's how we write it. And this is all new. The limit as x approaches 2 from the left. Do you think I want when x is greater than 2 or when x is less than or equal to 2? If I'm approaching 2 from the left, I want to look at that equation right here. I'm going to say 2 minus x. And we got to go see, is that equal to the limit as x approaches 2 from the right? Two from the right would be numbers that are bigger than 2. So you cool if I plug in that top function here? 3x minus 2. And how we evaluate limits now is we just plug that value in to my function. What is 2 minus 2 on the left side going to get me? What about on the right side? 6 minus 2 is going to get me 4. Does 0 equal 4? No. Therefore, these limits do not equal. Boom, we've got a discontinuity. As soon as something doesn't equal, we got to say discontinuous at x is 2. Let's try these 5 problems. Ooh, let's do the bottom one together. Should we do the bottom one together? Let's do it. Let's do 17 together. Boom. Whew. How about this? Let's not even do the graph. Let's not even do the graph. What's f of 1 going to be? Which one, top or bottom? Top one, right? X is greater than or equal to 1. So I'd have 2 times 1 plus 1. Final answer is 3. Does f of 1 exist? Yeah, it's 3. We got a point. This is new. Ready? The second thing says we got to compare the limit as x approaches 1 from the left to the limit as x approaches 1 from the right. Where did I come up with that 1? That number right there. My question is, which function goes with which here? As x approaches 1 from the left. It is going to be the bottom one, Ritz. He's saying, if I'm approaching 1 from the negative side, those things are going to be less than 1. So I'd put 4 minus x squared next to that guy. And we're curious, does that equal the limit as I approach 1 from the right? Thanks, Mateo, 2x plus 1. All we do is plug in that value. This is not a -1. This was letting us know from the left side. So we're just plugging in a 1 there. What would I get on the left side? 3. Does 3 equal 3? All right. The third step is your answer from the top equal to your answer from the bottom.
Yes.
Yeah. So what we would fancily say is f of 1 equaled the limit as x approached 1. 3 was 3, and we'd say it's continuous at x is 1. At any point, these don't equal or this doesn't exist, boom, you're done, and you say it's discontinuous at that point.